Finally, on to part 3 of our lesson on transformers, the calculations. So much of this I've already alluded to, taught some of it already, but let's take a closer look, get all the numbers in all the right places. So here's an image we've seen before. Okay, the relationship or turns ratio, so there's a term I've thrown out there a few times. The turns ratio between the primary and the secondary windings is what provides the change in the voltage or current. What I really want to highlight here on this slide are the labels, things you're going to have to become comfortable with. So N subscript P refers to the number of turns of the primary winding. How many loops does that coil make? Because ultimately that's what's going to determine the voltage. Okay, either the voltage there, not on the primary, of course, because the primary, by definition, is what's connected to the power supply. So the power supply is going to determine the voltage that we find in this coil. But we need to know the number of turns here in the primary coil to compare it to the number of turns over here in the secondary coil, which is capital N with a subscript S. Okay, so we talk about the turns ratio. What is the ratio? What is the comparison between the number of turns in the primary coil and the number of turns in the secondary coil? So N subscript P and N subscript S. Okay, then below that we have, let's go right down here to V subscript P. So that is the primary voltage. Okay, I will probably use a capital E rather than capital V. Okay, hopefully Pete does the same, bounces back and forth, and so you're comfortable with either notation. Okay, that's the primary voltage, and over here, almost buried, but still visible there, the secondary voltage, capital V subscript S. Okay, and then finally, we have I subscript P and I subscript S. So our primary current compared to our secondary current. So when we do the math, I underline this one and then I circled all the rest. When we do the math, these are the variables that we're going to be calculating for. Okay, primary windings, secondary windings, comparing the number of turns and the amount of voltage and the amount of current. Okay, so we have 6 variables here that we're going to be calculating for. So all of the values of the transformer are proportional to the turns ratio. So the turns ratio determines the proportion or the amount that the voltage and the current are going to change. Okay, so if we look at this one, we can see that the number of turns in the primary coil is 2,500. And the number of turns in the secondary coil is 500. Okay, so what is the turns ratio? All right, it's 2,500 over 500, okay, but we want to reduce that down to a nice simple number, and so it is 5 for every 5 turns, for every 5 loops in the primary coil, there is 1 loop in the secondary coil, okay? And typically when we talk about turns ratio, we write it like this. So it's 5 to 1. Okay, so 5 to 1 is the turns ratio. That's the way we would write that. That's the way we express it. Okay, that makes this a step down transformer. If we have 5 turns in the primary coil to every single turn on the secondary coil, we are stepping down by a turns ratio of 5 to 1, which means that the voltage is going to do the same. It's going to step down by a value of 5 to 1. So notice we have 120 volts on the input on our primary side. So the turns ratio is 5 to 1. The voltage ratio is going to be the very same. For every 5 volts we have on the primary side, we will find 1 volt on the secondary side. So 120 volts divided by 5 gives us 24 volts as the output on our secondary side. Okay, so it really is that straightforward. All right, it's completely directly proportional. Once we figure out the 5 to 1 ratio, okay, that's exactly what the voltage does as well. All right, step down transformer. So looking at it again, this transformer has 50 primary turns and 10 secondary turns. So we can say the turns ratio is 50 to 10. We want to simplify that. We always want to simplify that, and we get down to 5 to 1. same turns ratio, still a step down as we saw in the previous slide. Okay, so let's put some more numbers on here. Okay, so again, our voltage is going to step down by a factor of 5 to 1. So 1,000 volts on the primary side, 1/5 of 1,000 is 200 volts on the secondary side. Okay, now the current does the exact opposite. So I want to draw your attention down here to the 2,000 volt amps. Okay, VA is probably something you haven't heard before. VA stands for volt amps. And this is how we express power when we're talking about a transformer. Okay, now what's going on? So far you've calculated power in watts. And what is watts? Volts times amps. Now we're talking about power in terms of volt amps. Well, what do you suppose a volt amp is? Well, it's volts times amps. So what the hell? This is a really cool conversation, and you've got a lot of stuff you need to learn first. We're going to get there. Okay, before the term is out, I promise you, I will explain to you what the difference is between watts and volt amps. For now, let's just leave it an interesting mystery. Okay, but here's where I want to get with this. So the power is 2,000 volt amps. And so what must the current be? Well, here on the primary side, we had 1,000 volts. So we multiply that 1,000 volts by 2 amps to get our 2,000 volt amps. Okay, on the secondary side, we have 200 volts. Now we have to multiply that by 10 amps to get the same 2,000 volt amps. Sorry, you can't see that because of my ugly face, which is right there. Okay, still 2,000 volt amps. Power in must equal power out. So if the voltage steps down by a factor of 5, then the current must step up by a factor of 5 in order to get volts times amps to equal the same amount of power. Okay, had that conversation before, coming back to look at it again now with some more numbers involved. So that brings us to this. This is our fundamental transformer equation. So this will solve every equation, okay? And so when we break this down, I want to start here in the middle, and I'm not sure why this particular slide shows this in the middle. Typically, I would write this first. The number of turns in the primary side divided by the number of turns in the secondary side gives you a particular ratio or value. So far, everything we've talked about has been 5 to 1. Okay, and that is equal to the volts on the primary side divided by the volts on the secondary side. So again, there'll be 5 times as many volts on the primary side than there is on the secondary side. So E primary over E secondary is the same as primary turns over secondary turns. Look at what happens to the current. The current gets flipped upside down. Whoops, sorry about that little weave. Now the bigger number is up here on top. There's going to be 5 times as much current in the secondary of our transformer than what we find on the primary of the transformer, flipped upside down. Okay, so the voltage is directly proportional to the turns ratio. The current is inversely proportional to the turns ratio. It behaves in the exact opposite fashion. I think I just gave away the next slide. There it is. So transformer's power rating, which is expressed in volt amps, is always the same at the primary and the secondary. So remember, we talked about losses, we talked about efficiency. Now we're throwing all that out the window. We're just going to assume that the transformer is 100% efficient and that the secondary power is exactly the same as the primary power. Okay, it's not quite close enough that all this math works and we can carry on. So here we go. This next paragraph says exactly what I just said. Okay, the voltage change from the primary to the secondary is directly proportional to the turns ratio, and the current change from the primary to the secondary side is inversely proportional to the turns ratio. So that this equation works. This equation must always work. Apparent power, which is this weird volt amps power thing, the power must equal volts times amps in the primary values, and must also equal volts times amps using the secondary values. Okay, that equation has to work. Okay, cool. So we're back to the very same diagram. 2 2000 volt amps is the rating of the transformer, the size of the transformer. That's how we talk about transformer sizes, is in terms of volt amps. This one happens to be 2000. And it has a turns ratio of 5:1. Happens to be stepped down the way we've hooked it up, so that 1000 volts and 2 amps on the primary side and 200 volts and 10 amps on the secondary side in both instances multiply up to the 2000 volt amps. Okay, so notice what we've done here on this string of equations. So that right there is taking our primary voltage and dividing it by the turns ratio to calculate our secondary voltage. Okay, and then the second equation here does the exact opposite. It takes our primary current and it multiplies it by the turns ratio to arrive at our secondary current value. Okay, so those equations, all the numbers here, tie back into that fundamental transformer equation. Everything will always relate back to that. Okay, everything's always about the turns ratio. So let's give it a try. We are told that the primary voltage is 120 volts. Okay, we are told that the secondary voltage is 500 volts. Z is 1200 ohms. That's the impedance. That is, there's a word you haven't learned yet, have you? Impedance. Okay. You can see that it's ohms, so it's a resistive value. So for the time being, we can assume that that's an R, not a Z. Again, the explanation as to what the difference is will come eventually. Okay. We're going to need that for a particular reason here. Any idea what? We know the primary voltage, we know the secondary voltage. We've also been told the secondary turns ratio, the secondary turns, not the turns ratio. We've got to figure that out. That alone is not very helpful yet. But we don't know any current values. Okay, and I don't know how strongly Pete emphasizes this message. This is a message that I try to really lay on thick in my first level course. But what is it that determines current in a circuit? Okay, and usually the answer that gets thrown out at me is voltage. And that's partially true, right? Because Ohm's law says that the current equals the voltage divided by the resistance. And so voltage is certainly a part of it. But if we assume that everything's 120 volts, because in our house, everything's 120 volts, what is it that determines how much current is going to be on any particular circuit? And the answer is, how much resistance is there in that circuit? How many electrical loads have you added to that circuit? Okay, what is the resistance of the circuit? That is what determines the current. Okay, when you did your Ohm's law calculation, you usually thought of resistance as opposing current, which is absolutely true because that's how we taught it in the first place. But at a more practical level, okay, because when we add more electrical loads to our circuit, we are adding them in parallel, and every time you add a parallel branch, you actually provide more paths for current to follow, and it allows more current to flow. So when we're talking about more practical conversations about electrical loads and electrical circuits and current, we tend to talk about the electrical loads as demanding current. Okay, so rather than a resistor resisting current flow, adding another load demands more current. Okay, in actuality, it allows more current to flow, but we talk about it in terms of a demand. Okay, and so what determines the amount of current here in this transformer is the demand on the load, the demand on the power supply by the load. Have I completely confused everybody yet? Okay, let's bring it back to Ohm's law. Let's stick to the math. We know the secondary voltage is 500 volts. Okay, in this circuit, that is the power supply. That is the voltage being provided to the circuit. And Z, 1200 ohms, is the load in our circuit. So we can use Ohm's law to calculate current, right? I equals E over R. That will tell us what our secondary current is. We can use the two voltages that we have, the primary and secondary voltages, to figure out what our turns ratio is. And then that's going to allow us to then figure out what our primary current is. Okay. So I'm hoping maybe you've been doing the math while I've been rambling. If not, hit pause for a second, try to find those numbers for yourself, and then come on back. Okay, there are a few different ways you could have gone about this. But the first thing I hope you recognized is, what kind of transformer are we looking at here? Is it a step up or a step down transformer? It's a step up transformer. We have more voltage on the secondary side than we had on the primary side. Okay, let me hit forward here and get the answers to us for us. Here's the numbers. Okay, so the turns ratio happens to be kind of a clumsy number here, but for every 1 volt on the primary side, we have 4.17 volts on the secondary side. Okay, or for every turn we have on the primary side, we have 4.17 turns on the secondary side. So we knew that our secondary turns, our secondary coil had 800 turns. We can use this number to figure out how many turns we have on the primary side, which ends up being 192. Okay, we could go to Ohm's law to find out our secondary current. So we have 500 volts divided by 1200 ohms gives us 0.417 amps on the secondary side. Okay, it is going to be larger on the primary side. So working backwards through the transformer, the voltage got smaller. Working backwards through the transformer, the voltage was reduced, which means that working backwards through the transformer, the current must get increased. And so it increases by this 4.17, gives us 1.39 amps on the primary of our transformer. Okay, so there's an example of how we use the fundamental transformer equation to fill in the blanks and find out the voltages and currents for a circuit with a transformer in it. Okay, last thing we're going to look at, there's a number of slides here that talk about split windings and taps. Okay, and so we've talked a little bit about multi-taps. Okay, but it's really fairly typical for this arrangement that we're looking at right here. Okay, called a split secondary. Very often you'll get a split primary as well. Okay, where there are actually two coils. Okay, two secondary coils in this case. And oftentimes there might be two primary coils as well. So there would in fact be 4 coils rather than just 2. Rather than just a primary and a secondary coil, there would be 2 of each. Okay. Now the drawing shows the 2 secondary coils side by side. The fact of the matter is, in terms of the actual construction, these 2 coils are wound together. Okay. If you look at this, you can see that this is a shell type core. Right? And so we know in a shell type core that the low voltage winding is wound around that inner core piece, and then the high voltage winding is wound around it. Okay, so we've already got the 2 windings, the primary and the secondary winding, trying to occupy the same space. The 2 secondary windings are in a similar fashion. Okay, they're occupying the same space. They're not side by side the way the drawing shows it. Okay, they're actually wound around each other in addition to the primary, so everything's kind of all crammed in there together. The other thing that this slide shows us, and we'll see more of this in the next couple of slides to come, is some labeling. We haven't talked about any labeling yet, but notice that the secondary terminals are called X1, X2, X3, and X4. Okay, see, I just called it secondary, and in fact all of these slides assume that the primary is on the left and the secondary is on the right. Fact of the matter is, until we hook this up to a power supply and a load, we don't even know what the primary and the secondary is. Okay, but we can talk about high sides and low sides. All right, and the X label represents the low side of the transformer. Okay, so if you actually hook this transformer up as a step up transformer, the X terminals would be your primary windings. Okay, but in the case of a step down transformer, which is typically where we tend to focus our attention, okay, if you were to get a job with Hydro One and work on the generation side of things and the distribution side of things, then you would work almost exclusively with, well, no, but primarily, I suppose, with step up transformers. But as an electrician working at the consumer end of things, we're pretty much working with step down transformers. And so you will find that most electricians, myself included, fall into that habit very quickly of just assuming it's a step down transformer and the high side is the primary and the low side is the secondary. Probably not a safe assumption to make as an instructor, but as an electrician in the field working, that's what I'm working with pretty much exclusively, and so I fall into that habit very quickly. Okay. The low side of the transformer is labeled X. Okay, X1, X2, X3, X4. If it's a step down transformer, that will be your secondary. The advantage of this split secondary is it provides us with dual voltage. Okay, so we know that in our houses we have access to both 120 volts and 240 volts. Well, how do we accomplish this? We accomplish this by being fed from a transformer out on the street that has a split secondary. And the two secondaries are connected in series. So we can see here that there's a jumper between X2 and X3. Okay, which means the two secondary windings are connected in series. So if we connect to just one of the windings, the output of the transformer is 120 volts. But with those two voltage rises connected in series, the total voltage rise from X1 to X4 is the addition of those 220 volts to give us a total of 240. Okay, so this is a very real scenario. Every one of our houses is provided by a transformer that is constructed in exactly this fashion. Here we see the rest of the labels. This one happens to be a split primary, although again, the slide has fallen into the assumption that the left side, the high side, is the primary, and the right side, the low side, is the secondary with a step down transformer. We flipped it around so the split is on the high side, okay, and we have only X1 and X2 on the secondary side. Now, the thing that I really want to point out here, what's key on this slide, and we could have introduced this on the previous slides talking about the secondary, it's true for both, but we have taken these two lines and crossed them. Okay, and the reason for it will become apparent in the next slide. All right, but the result is when you read the H labels from top to bottom, it doesn't go H1, H2, H3, H4. It goes 1, 3, 2, 4. Okay, and this is extremely common in split transformers. Okay, you will see these labels all the time. It's not 1, 2, 3, 4. It's 1, 3, 2, 4. In the world of transformers, that's how we count. Okay, and part of it is a recognition that while we've drawn the two coils side by side, they actually occupy the same space. Okay, that's part of the reason for crossing them. Okay, but the other reason is, and let's move on to the next diagram. So this jumper we've placed between H2 and H3 to put the two primary coils in series, same as we did in the previous slide with the secondary. But the other option, okay, when we're hooking up two electrical devices, we have two choices. We can hook them up in series or we could hook them up in parallel. So let's hook up our two primary coils in parallel instead. And now we just need two bars, just like the first one, but another one, and place them there with 1 and 3 and 2 and 4. So now you can see that by crossing those two center lines, okay, we can comfortably recognize how these two coils get placed in parallel by jumpering 1 and 3 together to be one pole of, so if it's a DC circuit, that would be, say, the positive terminal, and then H2 and H4 connected to the negative terminal. Okay, of course, we're talking about transformers. Transformers don't work in DC. It has to be AC. Okay, but I'm trying to help you recognize, let me just draw this. If we were to complete the circuit out here to our, and I will show it as an AC power supply because it must be. And so there's how those two jumpers put those two primary coils in parallel in that circuit. Okay, so that's the reason why these two lines cross. There's a couple of reasons. One is to represent what's physically actually in existence, but the other thing is to make it more comfortable to just throw this jumper in here between 1 and 3 and 2 and 4. I'm pretty sure we've already seen this diagram. This shows us our tapped secondary. It could be a tapped primary. It doesn't matter. And again, all we have to do to understand the voltage outputs is to know the turns ratio. So we can see this is a step-down transformer, okay? And the numbers aren't really nice, okay? This is 480 volts. And if this was 48 volts, we could say without a calculator that the turns ratio was 10 to 1. Okay, since it's 45, it is slightly more than 10 to 1 because it's stepping down just slightly more than 10 times. Okay, so we won't worry about actually doing the math. I don't have a calculator handy, but that's the idea. And obviously, if we go to a different tap, what have I done? Sorry guys, my technology just gave me difficulty, but I was kind of done with that conversation anyway, because the next couple of slides carry on with the same idea. Okay, here's a multi-tap, but this time it's on the primary. And now we have numbers. I was struggling with the numbers in the previous slide. Things are much tidier now. Okay, and on the secondary side, we have 120 turns. Okay, and that output will be 40 volts if we hook up the primary side correctly. Okay, so that is to say that, so C at the bottom represents common, which means we will always connect to that common wire. The question is, what is the other wire that we're going to connect to when we build our circuit? So if we have 120 volt power supply available, then we want to connect to that first tap to ensure we get our 24 volt output. If we have a power supply that is 208 volts, we connect to the second tap, which has 1040 turns, to ensure we still get that 24 volts as our secondary output. If our power supply is 240 volts, then we need to connect to the top tap, giving us 1200 turns on our primary, so we still have the 24 volts as our output voltage. So this is the multi-tap transformer that I was talking about for the street lighting ballasts. Okay, I did tell you that they were auto transformers, so there is only a single coil, but the numbers that we're looking at here still work exactly the same way. Okay, we connect to different primary taps depending on the power supply available at that location to ensure that the output voltage on the secondary is always the same. The other way around, okay, maybe we have 120 volts as our available power supply and that's the only voltage available, but on our output side, we may want this transformer to function to feed different pieces of equipment that require different voltages. So we can use this same transformer to provide 12 volts to a particular piece of equipment, or 24 volts, or 48 volts. Okay, so again, we have a common here on our secondary side, 300 turns on our primary. The 12 volt output is 30 turns, so there's our turns ratio of 10 to 1, means the output voltage will be 1/10 of the input voltage, and that's our 12 volt output. Okay, or we can add an additional 30 turns for a total of 60 turns, which means our turns ratio now is 5 to 1, and the output is 1/5 of the 120 volts input. and so on. And that's the way it builds. I feel like this might be my last slide. So that is the math, and it all comes back to that fundamental transformer equation. So I will refer you back to that. That was what, about the 4th slide in. Okay, and that will always work for you. Okay, that will solve all of your transformer calculations.